Systems of linear inequalities. Let's consider the two inequalities in the introduction section. Unfortunately, the first two, analytical, methods used for solving systems of linear equations, elimination and substitution method, cannot be used in systems of linear inequalities, as here we have to find a region of the coordinates plane x, o, y where both inequalities are true. This region can extend at different orientations, so it is impossible to identify all values that belong to the solution set, without referring to a figure that shows the graphs of every single inequality. Therefore, we can solve graphically the system of linear inequalities. We have the following shown on screen. Obviously, as in all inequalities solved in the previous tutorial, when solving such a system only graphically, we must isolate the variable y and solve each inequality in terms of the other variable x. Then, we plot the graphs of each inequality and see where the double shaded area that shows the region where both inequalities are true extends. Therefore, only the last part of the solution reminds us of the existence of a system of linear inequalities. The rest of the solution looks like solving two different exercises containing a single inequality. However, we can still use the first two methods when checking the solution, especially when the corresponding equations form independent systems, i.e. when they have a single common point. We can check whether this point of convergence is the same as shown in the graph or not. Hence, we can write for the two inequalities in our example. We have the following shown on screen. We have the following shown on screen. This means the solution set includes the double shaded area below the lines y equals 3x over 2 minus 1 over 2, without including the line, and y equals minus x plus 4, including the line itself, as shown in the figure. We have the following shown on screen. Now, let's check whether points A and B in the introduction section belong to the solution set or not. Let's insert points A, -2, 0, and B, 2, 1, into the graph. We have the following shown on screen. From the graph, it is evident that point A does not belong to the solution set of the given system of linear inequalities, as it belongs only to the solution set of y less than or equal to minus x plus 4 but not to that of y less than 3x over 2, minus 1 over 2. On the other hand, point B belongs to the solution set of the given system of linear inequalities, as it is inside the double shaded zone. Let's check our graphical solution by making the numerical proof. We can take either the original inequality or the revised form used to plot the graph, as the result will not change. Thus, substituting the coordinates of point A, x equals -2, y equals 0, in the first inequality yields, we have the following shown on screen. While substituting the same point in the second inequality yields, we have the following shown on screen. Now, let's consider the coordinates of point B, x equals 2, y equals 1. Thus, when substituting them in the first inequality yields, we have the following shown on screen. And when substituting the coordinates of the same point in the second inequality yields, we have the following shown on screen. Therefore, only point B belongs to the solution set of the given system of inequalities, as when substituting its coordinates in the system of inequalities, makes both inequalities true. Remark: the graphing method not only makes us solve systems of linear inequalities, but it also helps us solve easier the corresponding systems of equations when the coefficients are such that they give rational numbers as solutions. Thus, instead of finding a pair of values obtained through complicated calculations, we simply plot the graphs and see what the coordinates of the intercept point is. Example: solve the following systems of inequalities. We have the following as shown on screen. Solution: First, we have to write all inequalities in the form y mx plus n, where contains one of the four inequality symbols, greater than, less than, greater than or equal to, or less than or equal to. It is worth to highlight the fact that we don't make this new arrangement to plot the graph line easier, as even in the actual form you can find 2 points that help plotting the graph. The reason why we isolate the y variable is to identify easier the direction of the solution zone. Hence, for the first inequality, we have the following as shown on screen. This means the solution set of this inequality includes the zone earlier, the graph line including this line as well. As for the second inequality of the system, we have the following shown on screen. This means the solution set of this inequality includes the zone earlier, the graph line including this line as well. Hence, the solution set will include the common zone that lies below each graph, as shown by the double shaded zone in the figure. We have the following shown on screen. Again, we have to write all inequalities in the form y mx plus n, where contains one of the four inequality symbols, greater than, less than, greater than or equal to, or less than or equal to. Thus, for the first inequality, we have the following as shown on screen. Thus, the solution set of this inequality alone includes the zone before the graph without the graph line. As for the second inequality, we have the following as shown on screen. Therefore, the solution set of this inequality alone includes the zone before the graph without the graph line. Hence, if considering the two graphs as forming an X-letter-like shape, the solution zone of the system will include the upper quarter of the shape, as shown in the figure. We have the following as shown on screen. That is all for lesson 10.4.1. To continue this tutorial, please watch 10.4.2, the minimum or maximum values of a system of linear inequalities. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.